I suppose the hardest part of inferential statistics is knowing which formula to use. Right? So when we're looking at our z-score, we often have this thing here, which stands for standard deviation, but it also stands for the standard error of population proportion and also the standard error of mean. So how do we know which one to use? How do we know whether we should just put in the normal standard deviation we're given, or whether we have to use this, or whether we have to use this? I suppose it comes to you with practice, but really the rule I would have is we use this one if we're just asked a very simple question like find the probability of something. Okay, so for instance, this question here. This one is a very simple question. We're just using our z-score to find the probability of choosing a student who obtained less than 75 marks. Okay, so that is a very straightforward z-score in which we have the mean mark, then we have our score, and then we have our standard deviation. Okay, and we get the z-score, and then we use our tables to get the probabilities. We generally use this one if we're talking about population proportions. Okay, so this question here would be a population proportion. So a company states that 75% of its users would recommend a face cream to a friend. We sample 500 people. 325 of them say they would recommend this cream to a friend. Conduct the hypothesis test. So there's nothing really about a mean there. Right? We're not comparing two means. We're not comparing two means, and generally it's population proportion. So we'll be using this and putting a value in there. And lastly then we have this one, and generally we use this and put that value in there if we are looking for if we're comparing two means. Right? So again, if we're looking for z-scores in relation to just simple population ones, we put the standard deviation in there. If we're talking about population proportions, we will put this in there to get a z-score. But if we're looking for confidence interval of a mean, well then we'll be using this formula. Okay, it'll make more sense when I'm doing the videos, but again it is practice. So here's one. A class does a test. Their mean mark is 60 with a standard deviation of 15. Find the probability of choosing a student who obtained less than 75. Okay, so that is a straightforward z-score. So we will be using this. So put in our figures. So our mark is 75. They say the mark is 60. They say the mean mark is 60, sorry. And the standard deviation then is 15. So that is 75 minus 16, which is 15 over 15, which is just one straight. Okay. Now let's sketch that. So remember, this is 0, negative numbers that way, okay, or negative z-scores that way, positive z-scores that way. This is positive, so it's up here somewhere. And we're looking, the probability of getting less than it, so it's back this way. And we know from learning, I suppose, that in order to get the probability of all of this, we will just look at the z-score, transfer our z-score into a probability using our tables. And if we look at our tables, I can see that one is 0.8413. So that's the probability of me choosing a student who obtained less than 75 marks. Okay, so there's an example of just a straightforward z-score. Next question. A company states that 75% of users would recommend a face cream to a friend. We sample 500 people, 325 of them say they would recommend it to a friend. Conduct a hypothesis test at the 5% level of significance to see if the company's statement is true. Right. I'm going to do this two different ways. I'll do it with a confidence interval method, and I'll do it with a z-score method. Okay. But by reading the question, we should see that we're not comparing two means. This is a population proportion question. Okay. So first of all, for both methods, I will state my H0 and I'll state my H1. So I'll say my null hypothesis, 70% of users would recommend, and the alternate hypothesis is percentage other than 75% would recommend. Okay, so the confidence interval method there would be the real population is somewhere between my p hat plus 1.96 root p1 minus p over n, and that's in our logbooks. And we have p hat minus 1.96 p1 minus p over n. So p hat is 0.65, and how I got that is I put the 325 on top and the 500 in the bottom, so divide one into both and I get 0.65% minus 1.96 over p hat. So that is again 0.65 multiplied by 1 minus 0.65 all over n, which is the sample, which is 500. So our real population will lie between that and my p hat, which is 0.65. Give myself a bit extra room. Plus by 1.96, 0.65, 1 minus 0.65 all over n, which is the population, which is 500 again. So that is 0.65 minus 0.041. Okay, that's when I put all of this into the calculator, I get this. 0.65 plus 0.041. So on this side then it'll give us 0.609. I'll put it up here actually, 0.609. And then on this side it is 0.691. Okay. So if I change this actually into a fraction, I get 0.75, and I want to see then if that lies within this. It doesn't. Okay. So I will reject no hypothesis. Okay. I change that into a decimal. Okay. I could also have changed these into percentages, okay, and that would have been 60.9% and that would have been 69.1%, and still that 75% would have lied outside it. Okay, so that's one method. The other method I could use the z-scores. So again, I would state my null hypothesis, but this time I would just take my standard error formula, P1 minus P all over N. Okay. I would throw my figures into it. I would get the 0.65, 1 minus 0.65 all over the 500, and that would give me 0.021. I would put that into a z-score then. So z equals all over 0.021, because remember, this here is a standard error question, so this we have to calculate, which we've just done, and we put it in for our standard deviation. Okay. So that's why we've done that. So our figure then was 0.65. The figure though up here is 0.75 changed into a decimal. And we get a z-score then of 4.76, minus 4.76. And we ask ourselves, does this lie between minus 1.96 and plus 1.96? And it does, it lies way outside that. Okay, so this minus 4.76 would lie way out here. So if it does, we will also say reject null hypothesis. Okay, just like we did over here. So same way really. Okay, either method is equally good. So in this video we have a population of tomatoes that have a mean weight of 56 grams and a standard deviation of 5 grams. So that's the whole population. So imagine a load of tomatoes, loads and loads of them. They have a mean weight of 56 grams, standard deviation of 5 grams. I take a sample of that population, which of 250 tomatoes, and find the probability that my sample has a mean weight of less than 56.5. Okay. Now, in this, we have mean weight. We're also looking for the probability of getting less than or mean weight. So this is one of these mean type questions, okay, which is one of these types. So we'll be looking at the standard error of mean because we're comparing two means. And if we do that, well, we will be looking at this formula, okay, to get our standard error. So with relation to a z-score, we'll be using this, finding out what that is, and putting it in here for our standard deviation. Okay. So here's our z-score, bearing in mind that we're comparing two means. So it's z x minus all over. Okay. So that is the mean we got, which is 56.5. That's what the population mean, which is 56. Okay. Over standard deviation, which is 5 all over root of the sample size 250, and that will give us 1.58. So there's our z-score. Quick sketch. Remember, this is 0. Anything positive is this way, anything negative is this way. This is a positive 1.58, so it's going to lie somewhere around here. We're asking what's the chance of getting less than that, so that will be back this way. And we know from our calculating our z-scores that how we get less than a number that's this side of the mean is we just get that z-score, open up our tables, and take the value straight off the tables. And that will give us 9.9 0.9429. Okay, so that's the probability. When I take that and I look into my tables on page 36 and 37 of the logbooks, that's the probability I get. Okay. Right, so in this question we have a random sample of 100 professional rugby players that were taken. The sample has a mean of 95 kgs with the standard deviation of 6 kgs. Construct a 95 confidence interval for the actual mean weight of rugby players. So this is a confidence interval of a mean. So the real mean will lie somewhere between the means we got plus 1.96. So it's just like the regular confidence interval, but remember it's a confidence interval of a mean. So we'll be looking at this now as opposed to this to get our standard error, right? Because this here gets the standard error of a mean and this here gets the standard error of a population proportion. So it'll be plus 1.96 standard deviation over root n, and again the mean that we got minus 1.96 standard deviation over n. We fill that in. The mean that we got was 95 kgs minus 1.96. So that's root n. The standard deviation was 6, and the population was 100. And likewise over here we have 95 kg plus 1.96. Standard deviation was 6, and we surveyed the sample size was 100. Just to make this clear now, it's just a coincidence that this is 95 and this is 95. Okay, so this 95 here is taken from this. Okay? Just, I know you know that anyway, but just to make sure. So that gives us the 95 minus 1.176, 95 plus 1.176, and that is 93.82 and 96.176. So what I'm saying there is, based on my sample and finding that my sample had a mean of 95 kgs, well, the actual mean of professional rugby players should be between 93.82 kgs and 96.17 kgs. Okay? So just notice here, it's the exact same as the other confidence interval of population proportion, except I'm using the standard error of a mean, okay, which is standard deviation over root n. Okay. So here we have a question then. We'll read over it first and we'll see what type of question it is. So over a long period it was found that the mean point score in higher level leaving cert maths was 60 points with a standard deviation of 12, and that is nationally. Okay, so at the national level, so all over Ireland. In Feathered, however, there was a sample of 40 past leaving cert higher level maths students was taken, and these had a mean of 62 points, okay, so higher. Is there significant evidence at the 5% level of significance that the students in Feathered score higher than those of the general population? So what are we comparing here? We're comparing the mean of, I suppose, the national students with the mean of Feathered students. So we're going to set it, we'll do it two ways. We'll do it a confidence interval way and then we'll do it a z-score way. Confidence interval way, same as the last question. So if the real mean lies somewhere between is our mean plus, minus 1.96 standard error of mean, our mean plus 1.96 standard error of mean. So let's do that. Okay, well, our mean is 62 minus 1.96. The standard deviation is 12 over the sample, which is 40, plus 1.96. Again, it's 12 and root 40. So that's 62 minus 3.71. And again, 62 plus 3.71. Here we have 65.71 and 50.29. So what we're saying there is based on our feathered scores, and our feathered mean lie between this and this, the real feathered mean. And we look then here and see does 60 points lie within that confidence interval? Yes, it does. Okay, so we will accept null hypothesis. Okay, and I suppose at the start, okay, I should have definitely put this in H0, H1. H0 would be feathered mean score. It's the same as national. Yes, the feathered kids are the same as the national. And H1 then, feathered mean score, not same as the national, right? And we see here that actually the feathered mean score is around the same as the national, okay, based on the 60% line within the confidence interval for the feathered score. So that's one way of doing it. The second way is via z-scores. Again, we should write up our two hypotheses, and we use our z-score then, so z equals over, again, it's our standard error of the mean. We can find out what this is. Okay? We can find out. We can throw it into the formula straight away, or we can just find out over here. Yeah, find out up here. So it's 40. Standard deviation was 12. So that equals 1.89. So Z equals 1.89 is on the bottom. And on the top then we have the mean the feather kids got, 262. And the mean of the national 60. That would be 2 over 1.89. And that equals 1.058, and then we ask ourselves, does that lie in between minus 1.96 and plus 1.96? Okay, it does, so we will accept null hypothesis. Okay, or we can say another way of saying accept null hypothesis is fail to reject. Alright? So there's really all the type of questions you can get. Well, there's also P-score questions, but that's on another video. But the hardest thing to do is for you to figure out which one of these you need to use. Alright? And that just comes with practice. Okay, thanks guys.